Hello everyone. Welcome to the third lecture of the 7th module, which is on resistive ramps. The disclaimers remain the same. So let me talk about this CB RAM in detail. So what exactly is a CB RAM? So CB RAM is actually an electrolytic cell. It's an electrolytic cell. You must have read about electrolytic cell in class 12, right, in chemistry. So here redox reaction takes place at the anode, and similar to that, here itself in CB RAM, there is a redox reaction, and that redox reaction is actually responsible for the memory behavior. How we shall see later. So it's based on, it's kind of an electrolytic cell. So it's based on actually redox reactions. So let me write that. So it's based on redox reactions. So it was first realized in 1991. So let me write it. So it was first realized in 1991. It's also a kind of RM. So here what happens is, it's also a MIM kind of structure where instead of insulator, what we have is a thin solid state electrolyte. So let me write it. So we have a thin solid state electrolyte, which is usually a chalcogenide glass. So chalcogens we already saw in PCM, like phase change memory. So what are the commonly used chalcogenide glasses? So we have germanium sulfide, we have GDOX, we also have tantalum oxide. So this is actually not a chalcogenide glass, but this is also used in CB RAM or PMC. So this thin solid state electrolyte, which is usually a chalcogenide glass, is sandwiched between two metal layers, two metal electrodes. And what are the properties of those metal electrodes? So the first metal electrode or the anode has to be an oxidizable anode or oxidizable metal. What are the typical metals that people use for it? So people use silver or copper. And what is the condition on the other electrode? Your cathode must be inert. So what I mean by inert? Inert simply means that it should not dissolve in the electrolyte during the redox reactions. So it should not be reactive with the solid state electrolyte. That is what I mean when I say that it's inert. The best part about this device is it's forming free. So you don't need a forming process. So energy wise, it's quite efficient. Also, it's bipolar. PMCs or CB RAMs are bipolar. You cannot have a unipolar PMC or CB RAM. So what happens here is you have a polarity dependent electrochemical deposition or removal of the anode material, anode metal, into the thin solid state electrolyte film. You can see here that you have AG layer, which is your first electrode. Then you have the GESE layer, which is also one kind of chalcogenide glass. And then you have the tungsten plug, which is the bottom electrode, which is not soluble in GESE. And can you think of why we have used this tungsten plug? Because here also it is integrated on top of the source drain contact plug. So mostly you will find CB RAMs also in 1T1R configuration. So here the TM image that I have shown, they have integrated this CB-RAM directly on top of the source drain contact plug, which is made up of tungsten. Okay. So what happens here? So if you look at its IV characteristics, you'll find that you start with a very high resistance state, then suddenly you reach a threshold voltage. Mind you that this threshold voltage is way smaller as compared to the R1 threshold voltage. It's only 0.2 volts, and then there is a sudden reduction in the resistance or a sudden increase in the conductance. And then here also we have to use a current compliance so that the device doesn't burn. And when we go towards the negative cycle and when we switch or sweep the voltage in the negative direction, the moment we reach a particular voltage, which is we reset here also, we see an abrupt transition to the high resistance state. So we started with the high resistance state over here. We switched from high resistance state to low resistance state here. Let me use a different kind of pen. So yeah, we started with high resistance state here. The moment we hit the switching voltage, we switched to the low resistance state, and we controlled the low resistance state resistance with the help of a current compliance. Then we again started to sweep it in the opposite direction. We hit a particular voltage, which is the V reset, and then after that we converted from LRS to HRS. So that is what we did. However, one thing you should keep in your mind that here, similar to the set, reset is also abrupt. So in your case of Oxram devices, your reset was not an abrupt process but a gradual process. However, here the moment it hits this reset threshold voltage, the resistance switches from low resistance to high resistance state, and V stop doesn't have any role. So there V stop had a role in deciding the final HRS just because the reset process was gradual. Even when you applied the voltages for a large duration, like even when you applied voltages beyond the V reset, then there was kind of a transition or switch, like there was a kind of dissolution of your conductive filament there. But here, even the reset is abrupt. So V stop doesn't have any role. Okay. So let me discuss about what exactly happens in this device. So what happens here is, if you apply a positive voltage greater than your set threshold, what happens? There are redox reactions. So redox reaction is set up at AG, GESE or whatever chalcogenide glass you have interface. And what that leads to is, it leads to, or what it does is, it drives the Ag ions into your GESE or chalcogenide electrolyte. So these Ag ions are kind of forced inside this GESE electrolyte, and then inside the electrolyte, what happens is, the Ag ions are reduced inside the electrolyte and form metal precipitates. Right? So this metal precipitate kind of forms, so let me write. So this metal precipitate leads to formation of a metal-rich conductive filament, metal-rich CF, which now connects the two electrodes, right? So this kind of metal-rich CF, so let me write that as well. This metal-rich cluster or metal-rich CF forms a bridge between the two electrodes, and hence the name conductive bridge RAM or programmable metallization cell. Now what happens if we apply a opposite polarity voltage? So if we apply a voltage of opposite polarity, these Ag ions are removed and the conduction bridge or the conduction filament dissolves rapidly. So this is the kind of working principle of your CB-RAM. Now, what are the typical ranges of ROF and RON here? So let me write that. So your ROF can be very high. So it can be between 10 to 100 gigaohms. And what about the RON? So RON here can also be really high. It can be from 0.1 to 1 megaohms. So what can you comment about ROF by RON? So your ROF, so in that Oxram, while discussing about RRAMs, I actually wrote RON by ROF, but it should be ROF by RON. So I won't repeat the same mistake here. So your ROF by RON can be greater than 10 raised power 5 to 10 raised power 6. So it is way larger than what is shown by. So let me write it. So the memory window is larger than RRAMs or Oxrams, right? So now let us discuss about the conductive filament over here. So the conductive filament or the conductive bridge can be as small as one atom or one ion of Ag or copper, right? Even that will lead to a conduction. So it is usually perceived as an internal wire which kind of connects the two electrodes. And what is so fascinating about this conduction filament? That at the verge of set, that is, the set process is about to begin, what happens is only a single atom. So only a single atom of Ag contacts the bottom electrode, right? So at the verge of set, only a single atom of Ag contacts the bottom electrode, and this kind of contacts where only a single atom is contacting an electrode is called a quantum point contact. This quantum point contact itself has a variety of, so it has got a very deep physics. It has got a very rich physics, I would say. And because of this, there is a quantization of conductance and all those things, which you will see in the later slides. I'll discuss that as well. But this kind of quantum point contact phenomena in your CB-RAM leads to a variety of interesting phenomena. So some of them we'll also discuss in this lecture. So not only this leads to quantum point contact, but it also tells you one thing, that it's highly scalable, right? Because it can be scaled to even one atom thin kind of a filament, right? So it's highly scalable. Now, once you scale it, what happens? Since we are discussing about scalability, let us talk about what happens when you scale it. So when you scale it, similar to what happened in Oxram, your ROF is going to increase, right? Why ROF is going to increase? Because the area is reducing, and R is rho L by A. Area reduces, your ROF is going to increase. Now, similar to Oxram, here also, RON depends on resistance of your wire, resistance of your conduction filament or conduction bridge or wire, whatever you call it, between the electrodes. So RON remains relatively independent of scaling. So RON doesn't change much. So let me see, RON doesn't change much. And can you comment about the threshold voltage here? Will that change with scaling? So the threshold voltage, VT set, also does not change with scaling. What is the reason behind that? So the reason is simple. It is a chemical property, and that is independent of scaling, right? Okay, so now that we have discussed about the scaling and all, let us talk about the phenomena which originate because of this quantum point contact. So because of this quantum point contact, what happens is there is a quantization of conductance. So let me just write it. So there is a quantization of conductance. So what that essentially means is change in conductance of CB-RAM close to set voltage is not continuous. Then what is it? It's kind of discrete. Why so? Because it's a single atom. So why so? Because it's, oh, my screen got frozen. Because it's a single atom which contacts the B. So the transport becomes not continuous but discrete. And what is the another property? The change in conductance at the verge of set occurs in multiplication of the fundamental conductance. And what is that fundamental conductance? So that G0 is nothing but 2E square by H. So this is the fundamental conductance, and close to the set where this kind of device shows quantum point contact, the conductance doesn't change continuously, but it changes discretely in multiplication or in factors of G0. And how people came up with this quantum point contact phenomena? So they just observed what exactly happens to this change in the conductance experimentally, and to explain this, they kind of came up with this quantum point contact phenomenon. So as I told you earlier, this field is like that only. First, someone experiences or someone observes something via experiments, and then they develop theories to explain it. So this is what precisely happened with this, and this is called quantized conductance. Quantized conductance. So this is an interesting property which appears in CB-RAMs. Now, when you have only single atom and all, this also indicates, I mean, this quantized conductance, it also indicates, let me write that, it also indicates ballistic transport. So what exactly is ballistic transport? So ballistic transport means that electrons travel without encountering any scattering event. It appears as if electron is fired from a gun. So electron is fired from a gun and it reaches the other electrode without any collisions. So there is a rich physics involved behind this quantum point contact, quantized conductance, and ballistic transport. And I would not go about it because there is not actually a, I would say, kind of platform or a course where I can discuss about this in detail. And here the plot on your left, this kind of also shows the effect of temperature on your resistance value, R on, R off, VTH on, VTH off, and everything. So if you see this, you'll find that it's kind of remaining nearly flat with temperature. I mean, the dependence on the temperature is kind of remaining nearly flat with temperature. So it has got a very small dependence on the temperature. All the parameters, performance parameters, have got a very small dependence on temperature. So that also let me write. So the different, not the performance parameters, but the device parameters. Device parameters are relatively independent of temperature. So what can be the potential application of CBRAMs? Where do you need a very high temperature of operation? I mean, where do you need your devices to sustain a very high temperature operation? It's automobile applications, right? So automobile application is somewhere, like automobile application is a very promising avenue for utilization of CBRAMs. One more place where Adesto, so Adesto is a company which has been working, so let me write, Adesto is a company which has been working with CBRAM devices for a long time. They have proposed it for space applications as well. Because in space also the temperature fluctuates very much. I mean, not fluctuates, but it's also very small. So Adesto has been using it for space applications. Two reasons. First, insensitivity to temperature. I mean, first it is temperature insensitive. And second, soft errors are not there. So it's resilient to soft errors. Right? Because they are ions. They are not electrons that they will be disturbed by, impingement of gamma rays and all. I mean, they get disturbed as well. However, a large amount of energy is required for that. It's better as compared to your SRAMs or DRAMs. So these are two reasons why Adesto has been very particular about using this for space applications. Now let us talk about multi-level capability, which is kind of the title of this slide. So similar to OXRAM devices, we can introduce MLC here by changing compliance current. So by tuning the compliance current, we can lead to MLC in your set state. So MLC in set state. And what does this do here? So you increase your I compliance, your conduction filament thickens. However, unlike OXRAM, V-stop doesn't play any role. So we have no MLC in reset. So here you can see that you limit the programming current and you limit the on resistance. I mean, you can tune the on resistance by tuning your programming current. So there's a linear relationship between the two, as shown in this graph. So you can achieve MLC in the set state, but not in the reset state. Let us talk about its endurance and all. Like the other property is in one line itself. So let's talk about endurance. So it has got a very high endurance as well. So endurance greater than 10/10 have already been reported. What is the other parameter? Speed. This is where your CBRAMs are much, like I would say, are much inferior to your RRAMs. In all the other properties, CBRAMs are somewhat superior to your OXRAMs. But when it comes to speed, the speed is limited. Why so? Because they are, the basic operation here is electrochemical reactions. So because of this inherent kind of operation, which is electrochemical reactions, which are inherently slow, the speed here is 10 to 50 microseconds. So it's close to flash or even higher than that. So this is where CBRAMs lack a lot, and that is why CBRAMs, I would say, have not become very popular in the market. Also, let me write that. Also, the moment we talk about filamentary conduction, we have to talk about what? Variations, right? Because it cannot be so that formation of filament and dissolution of filament are deterministic. So it's always the case that filamentary formation or CF formation, so let me write. So CF formation or dissolution has to be stochastic. You can actually reduce the level of stochasticity or variability by confining the electric field, by concentrating the electric field, or by changing the material, but you cannot make it very uniform. It has to be stochastic. So here also we have device to device as well as cycle to cycle variability, similar to our ramps. So that is another problem with this device. So speed, variability. What else? Nothing. Retention is also high. So let me talk about retention. So retention is also it also satisfies. So retention also satisfies industrial standard of 10 years. So that is not a problem over here. So with this, I finish all the lectures on resistive ramps.